Hi everyone, this is Group 8. We are Ayush Shah and Sichen Zhang. Today we're going to talk about Tarcil, reconciling scheduling speed and quality in large shared clusters. This paper is written by Christina Delimetro, Daniel Sanchez, Christos Kozirakis.
Hello guys, I'm Ayush and I'll start with the introduction part. So scheduling diverse applications in large shared clusters is particularly challenging. Recent research on cluster scheduling focuses either on scheduling speed, using sampling to quickly assign resources to tasks, or scheduling quality, using centralized algorithms that search for resources that improve both task performance and cluster utilization. So Tarcil is a distributed scheduler that targets both scheduling speed and quality. Tarcil uses an analytically derived sampling framework that adjusts the sampling size based on load and provides statistical guarantees on quality of allocated resources. It also implements admission control when sampling it's unlikely to find suitable resources. This makes it appropriate for large shared clusters hosting short and long running jobs. We evaluate Tarcil on clusters with hundreds of servers on EC2. For highly loaded clusters running short jobs, Tarcil improves task execution time by 41% over a distributed sampling based scheduler. For more general scenarios, Tarcil achieves great optimal performance for 4 times and 2 times more jobs than sampling based and centralized schedulers, respectively. Let me talk about the problems discussed here. An increasing and diverse set of applications is now hosted in private and public data centers. The large size of these clusters, that can be tens of thousands of servers, and high arrival rate of jobs like millions of tasks per second, make scheduling quite challenging. The cluster scheduler determines which hardware resources, like specific servers and cores, should be used by each job. Ideally, the scheduler should have three desirable properties. First, each workload should receive the resources that enable it to achieve predictable high performance. Second, jobs should be tightly packed on available servers to achieve high cluster utilization. Third, scheduling overheads should be minimal to allow the scheduler to scale to large clusters and high job arrival rates. Now, recent research on cluster scheduling can be examined using two dimensions. First is scheduling concurrency, and second is scheduling speed. So, scheduling concurrency, there are two groups of work. In the first, scheduling is serialized with a centralized scheduler making all decisions in this, and in the second, decisions are parallelized through two-level or distributed designs. Moving on to scheduling speed, there are again two main groups of work. The first group examines most of the cluster states to determine the most suitable resources for incoming tasks in a way that addresses the performance impact of hardware heterogeneity and interface in shared resources. The second group improves the speed of each scheduling decisions by only examining a small number of machines. Now over here, the image illustrates the trade-off between scheduling speed and quality. So in figure 1a, the PDF of application performance for three scenarios with analytics jobs of variable duration shows using Sparrow on a 200 server EC2 cluster is shown in the figure 1a. In figure 1b, it shows the PDF of job performance using the Quasar scheduler that accounts for heterogeneity and interference. Figure 1c shows the PDF of Tarcil. The scheduler achieves the best of both worlds, high quality and high speed decisions, making it appropriate for large, highly loaded clusters that host both short and long jobs. Moving on to background, there are three main types. First, we need to talk about the first is concurrent scheduling. Uh, Scheduling becomes a bottleneck for clusters with thousands of servers and high workload churn. Google's Omega, for example, has multiple scheduling agents that can access the whole cluster state concurrently. As long as these agents rarely attempt to assign work to the same servers, they proceed concurrently without delays. Next is sampling based scheduling. Sampling is a state of just a few servers, reduces the latency of each scheduling decision and the probability of conflicts between the concurrent agents, and is likely to find available resources in non-heavily loaded clusters. The next is heterogeneity and interference aware scheduling. Hardware heterogeneity occurs in large clusters because servers are populated and replaced progressively during the lifetime of the system. Moreover, the performance of task sharing a server may degrade significantly due to interference on shared resources such as cache, memory, and I/O channels. Scheduler can improve performance significantly by taking into consideration the job's resource preferences. Moving on to the Tarcil scheduler, let me talk about the overview first. So Tarcil is a shared state scheduler that allows multiple concurrent agents to operate on the cluster state. The scheduler processes incoming workloads as follows. First, upon submission, Tarcil first looks up the job's resources and interference sensitivity preferences. Tarcil performs admission control. Given coarse-grained statistics of the cluster state, it determines whether the scheduler is likely to quickly find resources of satisfactory quality for a job, or whether it should queue it for a while. Admission control is useful when the cluster is highly loaded. A queued application waits until it has a high probability of finding appropriate resources or until a queuing time threshold is reached. Then, for admitted jobs, Tarcil performs sampling based scheduling with a sample size adjusted to satisfy statistical guarantees on the quality of allocated resources. The scheduler also uses batch sampling if a job requests multiple cores. Tarcil examines the quality of sampled resources to select those best matching the job preferences. It additionally monitors the performance of running jobs. If a job runs significantly below its expected performance, the scheduler adjusts the scheduling decisions first locally and then via migration. Now, moving on to the analytical framework. First is we use the following framework to design and analyze the sampling based scheduling in Tarcil. So the first is resource unit. Tarcil manages resources at RU granularity using Linux containers. Each resource unit consists of one core and equally partitioned fraction of the server's memory and storage capacity and provision network bandwidth. Now, moving on to RU quality, the utility and application can extract from resource unit depends on the hardware type and the interference on the shared resources from other jobs on the same server. The scheduler obtains the interference preferences of an incoming job using a small set of micro benchmarks to inject pressure of increasing intensity from 0 to 99% on one of the 10 shared resources of interest. Interference preferences capture first the amount of pressure Ti a job can tolerate in each shared resource where I belongs between 1 and n, and second the amount of pressure Ci it itself will generate in that resource. Let W be an incoming job and VW the vector of interference it will cause in the n shared resources. VW is from ranges from C1 to Cn. To capture the fact that different jobs are sensitive to interference on different resources, we reorder the elements of VW by decreasing value of Ci and get V dash W, where V dash W is Cj Ck up to Cn, where C with Cj greater than or equal to Ck and Ck greater than equal to so on. Finally, we obtain a single value for a resource requirement of W using order preserving encoding scheme that transforms V dash W to a concatenation of its element, that is V W E N C is equal to Cj into 10 raised to 2 into 2 sorry, Cj into 10 raised to 2 into n minus 1 plus Ck into 10 raised to 2 into n minus 2, so on up to n. Now, for simplicity, we normalize VWANC in the range of 0 to 1 and derive the target resource quality for job W as shown in this function. A high value of quality target TW implements that job W is resource intensive. Its performance will depend a lot on the quality of scheduling decisions. We now need to find RUs that closely match this target quality to determine if an available resource unit H is appropriate for job W. We calculate the interference caused on RU by all other jobs occupying RUs on the same server. Assuming M resource units in the server, the total interference H experience on resource I is shown by this equation. Starting with vector VH, which is equal to C1, C2 all the way to Cn for H, and using the same reordering and order preserving encoding as for TW, we calculate the quality of resource H as shown by this equation, that is U of H is equal to 1 minus BHENC upon 2 raised to 10 raised to 2n minus 1, where U of H belongs to the range 0 to 1. Now, the higher the interference from collocated tasks, the lower UH will be. Resources with low UH are more appropriate for jobs that can tolerate a lot of interference and vice versa. Note that the ordering of Ci in VHENC follows the resource ordering in vector V dash W of the application we want to schedule, that is resource J, which is the most critical resource for job W, is ordered first. This ensures that RUs are judged with respect to the resources a new application is most sensitive to. Comparing UH for an RU against TW allows us to judge the quality of resource H for incoming job W. It is shown by this equation. right here. If Q equals 1, we have an ideal assignment with the server tolerating as much interference as the new job generates. If Q is within the range 0 and TW, selecting resource unit H will degrade the job's performance. If Q is within the TW and 1, the assignment will preserve the workload's performance, but it's suboptimal. It would be better to assign a more demanding job on the resource unit. Now, talking about the resource quality distribution, the figure on the side shows the distribution of Q for a 100 server cluster with approximately 800 RUs and 100 10-minute Hadoop jobs as resident load, where with 50% cluster utilization. For a non-demanding new job with TW, which is equal to 0.3, as shown in the left figure, and there are many appropriate RUs at any point. In contrast, for a demanding job with TW is equal to 0.8, which is the diagram on the right, only a small number of resources will lead to good performance. Obviously, the scheduler must adjust the sample size for new jobs based on TW. Moving on to assumptions and analysis. To make the analysis independent of application characteristics, we make Q an absolute ordering of RUs in the cluster. Starting with equation 5, we sort RUs based on Q for incoming job W, breaking any ties in quality with fair coin. Subsequently, we compute a uniformly distributed rank of resource quality D. For the ith value of sorted QD is D of I is equal to I upon N RU minus 1, with I belonging to the range of 0 to NRU minus 1, and NRU the number of total resource units. Because D is now uniformly distributed, we can derive the sample size in the following manner. Assume that the scheduler samples are resource unit candidates for each RU needed by an incoming workload. If we treat the qualities of this R candidates as random variables, DI, where DI is D1, D2, D3, up to dr, which is approximately between u of 0 and 1. There are uniformly distributed by construction and statistically independent from each other. We can derive the distribution of quality D after sampling. The cumulative distribution function, that is CDF, of the resource quality of each sampling, of each candidate is FDI of X is equal to probability of DI less than or equal to X, which is equal to X, where X belongs to the range of 0 and 1. Since the candidate with highest quality is selected from sample set, its resource quality is the max order random variable A, which is equal to max of the values from D1 to DR, and CDF is f of A of X is probability of A, where A is less than X, which is equal to probability of D of I, which is less than X, and D of 1 less than X, all the way up to D of R, which is less than X, which means the problem, which is equal to the probability DI less than equal to X, which is equal to X of R, where X belongs to the range of 0 and 1. Now, the figure 3 we have here shows the CDF of resource quality distributions under the uniformity assumption for sample sizes of R, that is 8, 16, 32, 64. The higher the value of R, the more skewed to the right the distribution is. Hence, the probability of finding only candidates of low quality quickly diminishes to zero. For example, for R is equal to 64, there is a 10 raised to minus 6 probability that none of the sampled RUs will have resource quality of at least D is equal to 80%. That is, probability D will be less than 0.8 for all resource unit, which is equal to 10 raised to negative 6. Now the figure 4 we have here validates the uniformity assumption on a 100 server EC2 cluster running short Spark tasks and longer Hadoop jobs. The cluster load is 70 to 75%. In all cases, the deviation between the analytically derived and measured distribution of D is minimum, which shows that analysis above holds in practice. In general, the larger the cluster, the more closely the distribution approximates uniformity. Now, for jobs that need multiple resource units, Tarcil uses batch sampling. For M requested units, the scheduler samples R into M resource units and selects the M best amongst them, as shown in figure 5a. Some application experience locality between subtasks for benefit from allocating all resources in a small set of machines. In such cases, for a sample resource unit, Tarcil examines its neighboring resources and makes a decision based on their aggregate quality, as shown in figure 5b. Alternatively, if a job prefers distributing its resources, the scheduler will allocate RUs in a in different machines, racks, and or cluster switches, assuming knowledge of the cluster's topology. The placement preferences for reasons such as security can also be specified in the form of attributes at submission time by the user. Now, sampling at high load. The equation showed here, that is f of a of x is equal to probability of a less than x, which is equal to probability of d1 less than or equal to x, and d2 less than equal to x, all the way up to dr less than equal to x, which is equal to probability di less than equal to x of r, which is equal to x raised to r. Where x belongs from 0 to 1. This equation estimates the probability of finding near optimal resources accurately when resources are not scarce. When the cluster operates at high load, we must increase the sampling size to generate the same probability of finding the candidate of equally high quality as when the system is unloaded. Assume a system with n RU, which is equal to 100 RUs. Its discrete CDF is f of a of x is equal to probability of a less than or equal to x, which is equal to x, where x is from 0 to 0 0.01, 0.02 up to n. For sample size r, it becomes f of a x, which is equal to x raised to r, and a quality target of probability of d less than 0.8, which is equal to 10 minus 3 is achieved with r is equal to 32. Now assume that 60% of the RUs are already busy. Now assume, if for example only 8 of the top 20 candidates for this task are available at this point, we need to set R is D, P, the probability of D less than 0.92, which is equal to 10 minus 3, which requires the sample size of R is equal to 82. Hence, the sample size for highly loaded cluster can be quite high, degrading scheduling latency. Moving on to admission control, when available resources are plentiful, jobs are immediately scheduled using sampling scheme. But when the load is high, the sampling size needed to find resources of sufficient quality may become quite large. Tarcil employs a simple admission control scheme that queues jobs until appropriate resources become available and estimates how long an application should wait at admission control. A sample indication to trigger job queuing is count available of RUs. This, however, does not yield sufficient insight into the quality of available resources. If most RUs have poor quality for an incoming job, the queuing may be preferable. Unfortunately, a naive quality check involves accessing the whole cluster state with prohibitive overheads. Instead, we maintain a small amount of coarse-grained information which allows for fast check. We leverage the information on contention scores that is already maintained per RU to construct a contention score vector that is from C1, C2 all the way to Cn. From the contention Ci, the resource unit experiences in each resource due to interference from neighboring RUs. We use locality sensitive hashing, that is LSH, based on random selection to hash these vectors into a small set of buckets. LSH computes the cosine distance between vectors and assigns RUs with similar contention scores in the respective resources to the same bucket. We only keep the single count of variable RUs for each bucket. The hash for an RU is recalculated upon instantiation for completion of a job. Updating the per bucket counters as fast operation out of the critical path of scheduling. Note that the excluding updates in RU status LSH is only performed once. Now admission control works as follows. We check the buckets that correspond to resources with quality that matches the incoming job preferences. If these buckets have counters close to number of RUs, the application is queued. In admission control, it may penalize resource demanding jobs for which RUs take longer to be free. To ensure this penalty is not severe, we impose an upper limit for queuing time. Therefore, the queued application wait until the probability that resources are freed increases or until an upper bound for waiting time is reached. To estimate waiting time, Tarcil records the rate at which RUs of each bucket become available in the recent history. Specifically, it uses simple feedback loop to examine when the probability that an appropriate RU exists approximates 1 for target bucket. The distribution is updated every time an RU from that bucket is freed. Tarcil also sets an upper bound for waiting time at mu plus 2 sigma, where mu and sigma are the mean and standard deviation for corresponding time until free time until free PDF. If the estimated waiting time is less than the upper bound, the job waits for resources to be freed. Otherwise, it is scheduled to avoid excessive queuing. Although admission control adds some complexity, it in practice it only delays workloads at a very high cluster utilization, that is over 80% to 85%. Now moving on to resource quality distribution. Validation of waiting time estimation. The figure 6 that is shown above shows the probability that a desired resource unit will become available within time t for different buckets with heterogeneous 100 server EC2 cluster running short Spark tasks and long Hadoop jobs. The cluster utilization is approximately 85%. We show the probabilities for R3 into 2 times large instances with CPU contention and R 3.2x large instances with network contention B and C 3 dot large instances with memory contention C. The distribution are obtained from recent history and vary across buckets. The dot in each line shows the estimated waiting time by Tarcil. There is less than 8% deviation between the estimated and measured time for an appropriate resource unit to be freed. In all experiments, we used 20 buckets and 2-hour history. This was sufficient to make accurate estimations of available resources. However, the bucket count and or history length may vary for other systems. Now, Sichan will talk about the Tarcil implementation.
Hi, I'm Sichan. I'm going to talk about the Tarcil implementations and also about evaluations. So here, this figure shows the components of the scheduler. Tarcil is a distributed shared state scheduler, so it does not have a central coordinator. Scheduling agents work in parallel, are load balanced by the cluster front end, and have a local copy of the shared server state which contains the list and status of all RUs. Since all schedulers have full access to the cluster state, conflicts are possible. Conflicts between agents are resolved using lock-free optimistic concurrency. The system maintains one resilient master copy of state in a separate server. Each scheduling agent has a local copy of this state which is updated frequently. When an agent makes a scheduling decision, it attempts to update the master state copy using an atomic write operation. Once the commit is successful, the resources are yielded to the corresponding agent. Any other agent with conflicting decisions needs to resample resources. The local copy of state of each agent is periodically synced with the master for about every 5 or 10 seconds. The timing of the updates includes a small random offset such that the master does not become the bottleneck. When the sample is small, decisions of scheduling agents rarely overlap and each scheduling action is fast. When the number of samples are increased beyond 32 for very large jobs, conflicts can become more frequent, which we resolve using incremental transactions on the non-conflicting resources. If a scheduling agent crashes, an idle cluster server resumes its role once it has obtained a copy from the masters, a copy of the master state. Each worker server has a local monitor module that handles scheduling requests, federates resource usage in server, and updates the RU quality. And here, this figure traces a scheduling event. Once a job is submitted, admission control evaluates whether it should be queued. Once the assigned scheduling agent sets the sample size according to the job's constraints, it samples the shared cluster state for the required number of RUs. Sampling happens locally in each agent. The agent computes the resource quality of sampled resources and selects the one allocated to the job. The selection takes into account the resource quality and platform preferences and any locality preferences of a task. The agent then attempts to update the master copy of the state. Upon a successful commit, it notifies the local monitor of the selected server over RPC and launches the task in target RU. The local monitor notifies admission control and the master copy to update their state. Once the task completes, the local monitor issues updates to the master state and notifies the agent and admission control. The scheduling agent then informs the cluster front end. And let's talk about adjusting allocations of Tarcil. For short-running tasks, the quality of the initial assignment is particularly important. For long-running tasks, we must also consider the different phases the program goes through. And similarly, we must consider cases where Tarcil makes a suboptimal allocation due to inaccurate classification, deviations from fully random selection in the sampling process, or a compromise in resource quality at admission control. So if there's a large deviation, the scheduler takes action. Since we are using containers, the primary action we take is to avoid scheduling other jobs on the same server. For scale-out workloads, the system also employs the simple auto-scale service, which allocates more RUs to improve the job's performance. Let's talk about the evaluations of this Tarcil. So we first evaluate Tarcil's scalability and its sensitivity to parameters such as the sample size and task duration. This figure shows the sensitivity of sampling overheads and response times to sample size for homogeneous Spark tasks with 100 milliseconds duration and cluster loads varying from 10% to 90% on the 110 server EC2 cluster. At low load, high-quality resources are plentiful and increasing R makes little difference to performance. As load increases, sampling with R equals 2 or R equals to 4 is unlikely to find good resources. R equals to 8 is optimal for both low and high cluster loads in this scenario. This figure shows the average and 95th percentile response times when we scale the cluster load in the 110 server EC2 cluster. The incoming jobs are homogeneous Spark tasks with 100 millisecond target duration. We increase the task arrival rate to increase the load. As we can see, at very high loads, scheduling overheads are dominated by queuing time and increased sample size. We now talk about comparison between schedulers. We compare Tarcil to Sparrow and Quasar. Sparrow uses a sampling ratio of R equals 2 servers for every core required, as recommended. Quasar has a centralized greedy scheduler that searches the cluster state with a timeout of 2 seconds. We compare the three schedulers on the TPCH benchmark. TPCH is a standard proxy for ad hoc, low latency queries that comprise a large fraction of load in shared clusters. First, we examine the case where TPCH is the only workload in the cluster. As in Figure A shows, the response time for 7 representative query types is shown in Figure A. And Figure A shows that the centralized scheduler experiences the highest variability in performance. Although some queries complete very fast because they receive high-quality resources, most experience high scheduling delays. And Figure B shows a setup where 40% of the cluster is busy servicing background applications, including other Spark jobs, long Hadoop workloads, and latency critical services like memory cache. Tarcil maintains an average performance only 6% higher compared to the unloaded cluster across query types. And next, in addition to interference, we also introduced hardware heterogeneity. Figure C shows the new performance for the TPC-H queries. And here, the figure on the top shows the performance of scheduled Spark task and resident man-cached load, or aggregate and over the time. And figure on the bottom left is the performance across 7,200 jobs on a 400 server EC2 cluster for the sampling-based and the centralized schedulers on Tarcil, normalized to optimal performance. This red figure, shows the cluster utilization with Tarcil throughout the duration of the experiment. And this blue figure shows the quality of resource allocation across all RUs. And the figure on the bottom right shows the scheduling overheads in Tarcil and centralized schedulers. Here we see on the top is the resource quality distribution for the sampling-based scheduler and Tarcil, with R equals to 8 and 16 RUs across different permutations of the EC2 scenario. Here at the bottom is the resource quality CDF for this. The left one is for sampling-based scheduler, and here the right one is for Tarcil. And we have presented the Tarcil, a cluster scheduler that improves both scheduling speed and quality, making it appropriate for large, high-loaded clusters running short and long jobs. We can see that Tarcil uses an analytically derived sampling framework that provides guarantees on the quality of allocated resources and adjusts the sample size to match application preferences. It also employs an emission control to avoid poor scheduling decisions at high load. We have compared Tarcil to existing parallel and centralized schedulers for various workloads on 100 and 400 servers clusters on Amazon EC2. We have showed that it provides low latency overheads, high application performance, and high cluster utilization. Moreover, it reduces performance jitter, improving predictability in large shared clusters. Okay, this is our presentation. Thank you for watching.